Hey everyone, welcome to another episode of the Haskell Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. Today, we're going to be continuing our discussion of type classes. Last time, we ended up going through some of the basic of the EQ type class, talked about what are type classes in general, how they implemented a form of ad hoc polymorphism into the Haskell type system, and how they are very fundamental to the Haskell type system. Additionally, we talked about how type classes are leveraged as class constraints on top of function declarations, and how to write our own type class instances. Today we're going to be discussing mainly a couple of the type classes that are available to you in the Haskell type system already, as well as a concept called type defaulting type classes and what that means. Also, in the process, I'm going to introduce this concept called type class inheritance and what that means exactly in the case of using type classes. Because class inheritance has a very specific connotation, especially for those coming from object-oriented programming and languages that implemented a Simula style of object-oriented programming versus a Smalltalk style, but let's not get into those discussions right now. Finally, we'll also discuss how instances are used in dispatching functions based on type. I think this is a particular important topic to understand and try to see because it gives you exactly what it is that Haskell does when your functions have their type signatures available to them, and especially if it is able to infer those type classes or those types, concretized types, because that would allow the underlying machinery to be able to dispatch on your types when they're calling your functions, and you don't have to necessarily worry about implementing that or manually declaring that stuff as you would in other languages where ad hoc polymorphism, especially at this level, is often used using interface inheritance, and you end up often having to have a lot of your classes implement the interface rather than the actual dispatching on those types themselves, which means you're actually upcasting to the interface. Haskell does that a lot for you implicitly behind the scenes, especially once you've established those type class instances for being available. But we'll again, get through that later on. First, let's talk about a couple of examples that are available to you inside Haskell. The first one we actually talked about quite a bit, but we never actually discussed what its type is as defined by Haskell, and that is the numeric type. We've encountered this number of times, and we've encountered this when we were discussing types in the first place, because integral types are very important inside of the system, especially when you're doing basic arithmetic. As usual, in order to get information about anything inside of a type, whether it be a type class or a particular type, you could use just :info to grab the type, or :I does the same thing. I'm using the full names, as I mentioned in previous episodes, merely so that you know what command I'm looking for, and you can actually go ahead and do, tab complete to actually see what is available to you in terms of commands to the GHCI REPL. When we are looking at numeric types and the numeric type class itself, there's a couple of things that should become now familiar to you. As with any type class declaration, it gives you a set of methods and signatures that it is expecting instances of the type class to define. One thing to note is the minimal. The minimal is the minimal implementation of the type class that you have to at least implement in order for an instance to be considered a valid instance of this type class. And then at the bottom, you see a couple of specializations. Those are instances that have already been defined for you for numeric types. So in this case, we have already numeric types the numeric type class being already defined in terms of implementation for the word concrete type, for the integer concrete type, and so forth. A couple of these functions, once you have this information, you could just leverage. I mean, we've used this already. You could do basic addition by just doing this. Behind the scenes, you're going to get the inferred type that the underlying Haskell type system ends up finding before it goes and dispatches, because what it does is it infers the types, and then it looks up what type class to actually leverage, find the implementation for that particular operation, and then dispatches on that operation. Again, this is all related to the type dispatching mechanism that's inside Haskell, but it's important for you to know how all that kind of works. And we're going to go into more greater detail about it as we go on in today's episode. One thing to note is that's particularly important versus stuff that we've seen before is there is a from integer and a from integral type class. This is related to just implementing, what was it? It was, let me just pull this up again. From integer, we already kind of know that it just takes in an integer and just returns whatever type, underlying type it's getting. So if you do from integral and you try to pass in an integer type, well, technically an integral type is more general than an integer type, so it'll go ahead and leverage that. From integer and from integral are essentially similar functions in terms of how they implement this with relation to a numeric type, but integral is actually a different type class altogether. Okay, and we're going to see that in a minute. Bottom line, when you're using a lot of these type classes, especially starting with the numeric type, you need to look at the signatures here as they were defined. And again, just to give you a review, operators are defined usually like this, especially so that they can be used in prefix notation, although they have an infix association with it, so you can use them as a normal infix operator. Then you have this defined as colon operator that allows you to restrict the type signature. It's actually, you're actually specifying the type information here. On the right-hand side, we have our standard type signature, which in this case is a curried function that takes in two variables and returns a variable of the same type as its variables that are passed in. And again, as a review for those joining us, the little a stands for a generic type variable being available to you. So I introduced from integral, but I didn't actually introduce the integral type class. So let's see this integral type class to get more information as to how it differs exactly from the numeric type class. Remember these basic operations. These are your basic arithmetic operations: negation, absolute value, signum, from integer. Right? These are pretty much the same for all numeric types. Okay. From integral actually is a type class that introduces something that we saw last time when we were writing our own type class. Specifically, when we're restricting the type class, we have these things called class constraints. An integral is a type class that actually ends up using this in a much more complex way than um, what we've encountered in last week's discussion. Integral specifically implement, as you could probably tell from the method signatures here in its interface, in its declaration, these are implementing all the operations related to essentially division arithmetic. All right, so you got your quotient and your remainder, your div and mod operators, and then you have these two tuple based functions, quote rem and div mod, both of which actually implement essentially quote and rem and div and mod respectively, but they return the return values in has multiple values, so you end up getting a single tuple that you can end up doing like first and second. There might be some cases where you may want to end up doing that, so this is a much easier way to actually have these product types already available to you. So an example of this is if you do quote, 10.5, well, let's do 11.5, and then we do rem 11.5. If you need both of them, you could just use quote rem 11.5, and you can get that, in a single operation instead of actually having two different lines and then creating the tuple yourself. Then we have a operation called toInteger, which allows you to take in, and I was going to show this to you, but I don't know if I can actually use it. If there is a method that you want more information on, let's say we wanted to get it for toInteger, we could simply where is it? It is there's actually a Google search that's built into do Emacs with Dante that you could then just use to actually grab information. The one thing, and the reason why I'm just showing you the query default is if you hit enter here, it ends up popping up your web browser and actually giving you the search results. And unfortunately, I'm not actually sharing the search results. Sorry, I haven't actually hooked it up so it can redirect my browser, not to my default browser, but to the built-in Emacs browser, so you can actually see it inside there. But you could certainly do that. And what does toInteger do exactly? That one was, I think it's, if I pass in any type, it just either truncates or does something. Let's see what happens if I use toInteger. Ambiguous type rail arising from toInteger prevents the constraint from being solved. Okay, got it. So I have to use probably like a fractional type or something like that, and that is an integral type. Let's see what happens. What? Interesting. Okay, so for some reason this is not doing what I expected to do. It has to take a real, and it has to be enumerable. Okay. We'll get into this this particular function and why it's doing what it's doing in a minute. But first, I want to discuss this signature here because we've talked about it a bit in last week, but we didn't really dig into what this is the signature is all about. So, Typeclasses, as you know now, provides essentially a set of constraints on what concrete types have to adhere to in order for a particular set of operations to be executed, or in this case, for a particular new type class to be instantiated. Okay. Type classes themselves are additive, and what that means is they are only adding additional information about what a type class needs to implement. What an instance needs to implement in order for it to be a valid version of this particular type. Okay, and I'll give you a brief example. Right now, we're seeing here real and enum, which, if you recall, real is for type classes that are essentially like floating point numbers or double numbers, and so forth. And enumerable is it can be, as the name says, enumerated. The one thing to note about the real type class, and I think it'll be easier to actually show this, is to show this. Real itself is has additional class constraints, all right, which means integral already has these additional class constraints by simply having that as a constraint in order for integral to be instantiated. And what that is a real number should be both a numeric type and it should be an ordered type, which means it can be ordered in some way or shape or form. It implements the comparison operators, okay? And to really drive this home, ordered, okay, which we'll be discussing in more detail in a minute, but I need to show this to give you drive this idea of inheritance. Ordered itself is actually implemented as requiring whatever concrete type you're using to be using to implement the equality type class. Okay, so it all trickles down, and what type class inheritance does and what additive and type class inheritance does is essentially each one of these are adding a new set of operations on top of what's already been defined. Okay, what that means is ordered does not override the methods that are defined in EQ. It actually uses them. Okay, a real does not actually override whatever is defined by numeric or ordered. It just uses them. All right. In this way, we are avoiding classical ambiguity problems that ends up occurring in programming languages that implement multiple inheritance. Because the rule is all new interfaces cannot override even if they implement existing interfaces. They're only adding to the actual interface signature, if you will, all right? The set of methods that an actual concrete type has to implement in order for it to satisfy all these class constraints and therefore become a instance of this particular type class, right? This is particularly going to bite you if you're not recognizing this particular thing. So if you end up, for example, implementing the integral type class, okay, just beware that when you do so, you not only have to implement all these for your particular class, unless you're using word, integer, and int. You have to also implement whatever real and enumerated needs in order for that to do their job, right? In enumerated, we've seen ordered. Okay, let's see. I mean, we've seen real. Let's see enumeration. Enumeration, you're going to have to actually implement all these methods as well. What's the successor? What's the predecessor? To enum, from enum, and so forth. All right. And again, as with every type class, there's a minimal subset that you could implement. And what it does is if you implement just these two functions, everything else can be derived from those two functions. Okay. So the next class, actually, let me stop here for just a minute. Are there any questions regarding this? What error? That's an interesting question. We got a question that asks, what error does Haskell throw if we have an integral type that does not implement one of the type classes that's required, like EQ and so forth? I'm not entirely sure. That's actually we could try that. Let's do some experimentation here. So we have let's see. So let me bring up the integral type class again. So this needs to have quote when actually we could just create a data type that doesn't have an integral implemented. My guess would be is it's going to be related to what we saw before. It's going to do a lookup error and say that it actually fails. In fact, I think there's an example of this when we go through the fractional type class, but let me double check. But that's kind of what I'm thinking it's going to be. Let's see this. Let's see, instance integral I have something that I can actually create an integral instance of. Well, we have this one, which we could probably add types to, which is because we have an EQ already available, we might be able to leverage this. And then since we're not going to implement real or enum, it might actually throw an error, but we'll see. Rainbow color. What is the minimal? Okay, where? And we're already getting an error. What is the error? One more argument to integral. What did I mess up in terms of instance? One more argument to integral. Oh, we need to actually put in the real. Wait, do we need to specify this? We shouldn't have to specify this. You'll see. this error. What is this error? Non-type variable argument. Yeah, that's what I figured. Shouldn't have to do that. Here we go. No instance of... Okay, so this is the error that you would kind of get as you are defining your type classes for a type that doesn't implement any of the other class constraints, okay? When you load this, obviously, obviously into your REPL, you'll end up getting this error, which is telling you that the superclasses have been violated and you might get undefined behavior, because obviously you're deferring the type errors until the first time this integral definition is actually ran during the execution of a function, and then we'll throw up that error saying that, sorry, I can't actually instantiate enum rainbow color and so forth. Does that make sense? This is kind of what I was expecting, but I didn't realize that it will happen so early on. It looks like it's because, at least in the Emacs environment that I'm using, Dante, since it hooks straight into Haskell, it'll compile the code automatically and give you these warning messages. And if you want to make them errors, you could certainly add that -W, deferred type errors, and it will go and do it. Cool. Any other questions from folks? Okay. Let's move on. So the next one that we're going to go and review is fractional. So we saw real implements our division for integral types. We saw that the integral type class implements essentially the division operators for integral types. We saw integer provides all our arithmetic operations for integer types, but there's obviously things that we want to deal with specifically with rationals that are not indicated by either. Particularly the division operator that we're all accustomed to using, as well as some operators that would, for example, give us the reciprocal of a particular function or a particular value. All right. So for that, we have the fractional type class, which implements the division operator, the reciprocal function, as well as from rational, which will convert rational to any other type. So, in reciprocal, if you guys recall what a reciprocal is it'll take in any type and essentially convert it into 1 over its value. So in this case, 2 becomes 1/2 and so forth. This is what's often used for dealing with a lot of rational arithmetic inside Haskell. There are other languages that also have rational types itself, but this type class allows you to pick any sub-representation, and as long as it implements the numeric type class, it can be used to define these methods for the particular type, so that it can actually be looked up and then dispatched on. Again, all the type classes that I've introduced now and that we've been discussing up until now, with the exception of numeric, are all examples of this type class inheritance concept that I've been discussing. They're all additive. They're adding a class constraint saying that you need to, in addition to the methods that are part of this interface, you're going to have to implement those other methods. And we saw what would happen if you don't. It will end up attempting to infer that these methods have to be defined, can't find them, it throws up a warning, and in many cases it will throw up an error inside the REPL when you try and instantiate it during the course of some function execution that you may have defined later on in your program. So the one thing about fractional, and this goes also somewhat true for even integral types, is that fractional is a subset of numeric types, as you guys can probably guess from remembering your mathematics, your math class from yesteryear. It is although it is a countably infinite set, to use the technical math term. Fractional numbers do apply to a fewer set of numbers than numeric would, because numeric includes all the reals, which could, in machine arithmetic, includes both the floating representations as well as the double representations, as well as the integer representations for numbers, and based on that, you have word size and so forth that you need to account for too. The reason why this is important is that means that the fractional type class only applies to a set of functions that themselves are numeric, but not all numeric values would end up have to have functions defined in the fractional types class, because not all numerics actually fit the definition of being an instance of fractional, right? This is something that as you are developing larger scale Haskell programs, or even as you're developing more and more into Haskell, you'll end up getting this intuition as, okay, I should be using this more restrictive type class than this type class, and you'll end up actually eliminating certain classes of errors just because of the fact that you've now categorized what operations you really do need to define in order for your program to be correct, right? And we could see this actually with a couple of functional examples, right? Let's go ahead and define a simple function that will create us and this is an example from the Haskell book that I thought was particularly important to go through, chapter 6. If you're using the screen, section 6.6 on the numeric type class, okay? Subsection on the fractional. Okay, this is a function that basically takes in two arguments and then it divides the arguments and adds one to them. Okay, really, I think this function would be better appropriately named as divide and increment than divide and add. Now, we could see already, because again, as with anything in running our Haskell compiler against this file, it's going to warn us that we don't have a signature against this. So let's explicitly define the signature here, right? And let's define it as being a function that essentially requires all of its types to be numeric types, but then we have a standard function that does this. Okay. Automatically, you start seeing some errors being thrown here, and let's see what happens when we try to load this file. Okay. You'll see this error saying that we cannot deduce a fractional type based on the use of division here. Okay. Because it's coming from the context that our types themselves are very generic. They are numeric types, but numeric types themselves don't actually implement the division operator. All right, you can't actually define it like this. Now, there's a couple of ways of obviously fixing this. All right, we could change the type signature, because really, since we're dividing it, we could do fractional. All right, and this will end up giving us the same issue, no issues. It will load up okay. All right, but if we know that our data our types that we're going to be using for the lifetime of the program are all going to be numeric. We don't necessarily need to know that it's a fractional, and we're not going to necessarily divide this information. It gives you a hint, essentially, to the fact that maybe the algorithm itself might need to be changed, okay? So you could certainly do that, and the type signature doesn't change, the implementation does, okay? So instead of doing this, you might end up saying, okay, you know what we really need is something that does subtraction rather than fractional. So in this case, subtraction is defined for all numeric types, so we can go ahead and do that. And then we can go and add, subtract, then increment, taking 2 arguments and then subtracting the 2 and then adding 1. And this will show you that the type signature may be determining how one might implement a function versus implementing a function and then determining what the type signature necessarily will be, because you might end up getting differing well, first off, you will definitely get differing implementations if it turns out that you're using a more generic type based on what you've ended up encountering in terms of your experimentation of the data that's being passed into your program. But obviously, as you can see in this case, it's more subtle than that. It basically allows you to determine whether or not are you more concerned with data being passed in, restricting to a specific type class, versus actually implementation details. Okay. Here we're taking the most generic algorithm, because we're using numeric, and numeric is a superclass of fractional. And here we're being more restrictive, and we're creating a special case almost in order to implement an algorithm that adheres to that special case, which means you may end up having to actually implement it for other cases as well. Both are perfectly legitimate approaches to actually implementing code. But it's one you have to go and obviously determine for your use case which one would be more appropriate. All right. The astute observer, who's getting used to the type classes and trying to use all this stuff, might ask, well, wait a second, why not just, instead of doing fractional here, why not, given our original signature, go ahead and do an additive fractional type like this, right? Well, although technically this is legitimate, all right, because fractional is associated with the division operator, and the division operator is implemented as part of the fractional type class. Recall, fractional is more a restrictive version of numeric, all right? So by having fractional there, you're already having to adhere to the numeric type class constraint, because that's what's necessary in order to instantiate the fractional type class. Okay, so by doing this, you're actually being redundant. You're saying this is not only numeric, but it's also fractional. They're not actually disjoint sets you're dealing with. You're actually saying, I want specifically this subset of this larger set of objects that adhere to this interface. So it's absolutely unnecessary to do that. You could just keep it like this. Because again, by doing fractional, we're automatically dealing with the numeric type class. All right. So let's stop for a minute and start talking about this class constrained polymorphic values that we're getting from the type classes. What exactly does it do again? So recall that in this approach to ad hoc polymorphism, what happens is the type system actually has to take a value and resolve it to a concrete type. And what this concrete type that during the inferencing process has to go through is essentially a check to make sure that the concrete type is defined for all the required type class instances that are required by the class constraints that the function signature is providing us. Okay, recalling this as being an example of such a class constraint, right? If, for example, we're talking about something that's fractional, we know then if we're dealing with a concrete type, that any concrete type that's being passed in, we know that it not only has to implement the fractional type class, it also has to implement the numeric type class in order for the type class to actually be instantiated correctly, right? One example of this also is if we end up inferring specific things like the fractional and the type classes that are being provided by the concrete type, certain conclusions can actually be made by the type system. So, for example, if we know that something that needs to be fractional, which again, being fractional means that it has to implement the numeric type class, which means it's both fractional and numeric. We know that the concrete type instantiation cannot be something like, say, a fixed int. Like, it can't be an int because int doesn't necessarily implement the fractional type class itself, right? So it can infer from the information that is provided through the type inferencing process what a type can't be, and it can throw the appropriate error, all right? Ordinarily, type inference gets all this kind of like squared away, ends up checking to see if it can be of a particular type, say like an integer, and then forces that polymorphic value to be like the return value, especially in the case of places where you're using all the same type to be that kind of concrete value, right? So you don't have to actually declare that your type is provided here. And you don't have to declare that the return value must be of this type, although you can certainly do so, and I'm going to just review that particular thing in a minute. But the one thing to know is in cases when you're doing interactive development, okay, and this is where it becomes very important, where this actually occurs, and we saw this last time when we were dealing with the my identity example with where it ended up giving us some errors saying that it couldn't look up a particular type that we were passing into my identity. And as it turned out, it was because of the fact that it was type defaulting in the REPL to being a particular type, and there were two definitions that actually fit that concrete type. All right. That's what's called type defaulting. Okay, so in interactive development, where you don't specify a concrete type for a polymorphic value, in those cases, the type class itself will default to some concrete type that fits all the constraints that were provided in signature, right? And this is already set in many cases with respect to the standard library in the standard library itself, all right? They will provide this, all right? An example of how type defaulting might work that's not as convoluted as our my identity type class is just simple division. Okay, when you define when you run just this simple division, okay, and you do type 1 divided by 2, actually type of 0.5, you could see where. How do I get the defaults? That's not it. One second. Oh, right. It was actually defaulted in things. You can see behind the scenes that this division operator, when you divide 1 divided by 2, it's going to return you a essentially something that implements the fractional type class. Okay, which if you look up in the Haskell report or in Google, the fractional type class defaults to using doubles all the time, just because it's the largest precision floating point number that will prevent overflow or underflow, and prevents certain types of precision errors that could occur by not using a much larger precision value. Much larger precision representation for a floating point. But one of the things that Haskell provides you, if you remember, is the type assignment operator. All right, the colon. We've been using it this entire time. All right, this when we're declaring our functions. And remember, we've actually used this in the past to actually restrict our types when we were playing around in the replit as well. So we could do this, and the reason why we would do this is by restricting the type information. We are, I think it'll be easier to first, let me add this and do that. So 2 fractional divided by 2 being a float, and you'll see that this is going to return itself as being an instance of a float. Okay, and this is the same if you're using floats or doubles. You can actually restrict it to being a specific double. In the case, the difference of using the type assignment and restricting to double and the just without the type assignment, the reason why it's giving you a different signature, although we know that the default type is a double, is because technically speaking, the type inferencer inferred that it is of type fractional. It's not because that it didn't end up using a double at the end to construct this value before returning it. It's because the inferencing engine says, okay, this is a fractional type, but we can't determine what fractional type it is. What's the default fractional type that we can use? Oh, we can use a double representation to implement a fractional type class. Okay, we're going to construct a concrete version of this double representation, because that will still satisfy the class constraint, and we can go ahead and return it as is. Whereas here, we're explicitly saying, no matter what you infer, I want this return to be as a double. All right. So that's us being a little bit more restrictive than what the type inferencing engine is going to give us. We can also, say that this is a rational, and we'll go ahead and do the same thing for rational numbers. Again, you can go and look into the type definitions for default types at your leisure, and you can see each of these have their own default type classes. So like numerics, I have numerics has defaulted to default type is integer, and reals also integer, and so forth. There's so many of them. I'll defer you to both the documentation, what's in the book, as well as in the Haskell book, as well as what's in the Haskell report to figure out this thing. But these are just a couple of examples. You can see this in this notation as to what is your particular type. So in the case of our example, we were using fractional, and defaults to double, and that's what's available inside the Haskell report. When you're reading this, just remember that numeric, real, and all the types in the first argument default, these are your type classes, and the integer and doubles and stuff are concrete types. All right, that they're defaulting to. Okay. So what this does is behind the scenes, in the again, this is all restricted to interactive development because you have a couple of other stages when you're compiling code inside. Uh, 1 second, there was a question regarding. Hangout link. It's available for folks to join us if they want to. Okay. So what happens is in the REPL, when it has these default type classes, these types available for each of these type classes, is the REPL essentially changes the function signature ever so slightly to the default types. Okay. So if you don't use the type assignment operator, for example, like this, like what we're seeing here with float, double, and rational, it will change the function signature to use doubles, and then you'll go ahead and run this code as if all the numbers were doubles. But if you've restricted it to a particular type, like rational, float, or double, that type variable is substituted after it gets checked against the fractional type class. If it satisfies itself, the signature then changes to dealing with only floats, and then you'll get the correct machine code itself. The same idea can be applied to any of the functions that we've seen in any of the type classes that we've encountered so far. So like div, for example. Div, what it will do is it'll check the type that's being passed in. Let's say if it's an integer, we know an integer implements both the real type class and the enum type class. It is because it's enumerable and it is of a real value, meaning that it implements the numeric and ordinal, and also implements the two rational functions as well. And so what the type inferencer will do is, again, just like if you look at other languages like, say, C++ and stuff, it does a form of like template instantiation, but really what it's doing is at the time of a compilation and construction of the final value before evaluation, it changes the signature so it can do some additional type checking of the actual concrete values that are being passed in. Okay. When you're dealing with concrete types, okay, so when you're dealing with integer, when you're dealing with your abstract data types that you provide, let's say structs, when you're dealing with, say, some of our stuff like that we've encountered earlier, like our data, our pair, or our trivial, or our rainbow color, okay, you don't need at that point to leverage a type class constraint in your function signature, okay? And your Haskell actually does this nice job of actually telling you that it'll say that this is superfluous, all right? This is unnecessary. But if you're trying to implement a more generic algorithm, all right, but you know that certain properties have to be satisfied in order for this algorithm to execute correctly, then what you may end up wanting to do is end up implementing your function using with the type class constraint instead. All right, so don't write, given a function f integer arrow integer. Instead, you may want to write, given a function that you're trying to define, you may end up wanting to write something like this. Okay, if you know that you're going to be dealing with a lot more different types of numeric types. All right. Using polymorphic values, and this is the reason why actually in Haskell, if you're using a polymorphic value and you don't allow Haskell to infer the specific type and the default rule, GHC will end up start complaining about not having enough type information to actually do the right thing, and it will abort compilation, or it'll abort evaluation, function evaluation, in the case of using it in the REPL. Okay. Um, One of the things that this ends up driving, okay, is that if you know your data types ahead of time, all right, which is rare when you're writing large-scale programs, but sometimes you do know it, like especially if you're writing, numeric programs like calculators and things like this. You could certainly restrict your types ahead of time, and then use, say, the ability of Haskell to go and restrict those signatures, that operations that are being used against those data types. It allows them to get generated ahead of time, and provide some optimizations. An example of this is let's say that we have a value 10, right? Although I don't think you necessarily need to provide. Oh, you have to actually provide. Let's say this. Okay, we don't need to actually put this in, right? Because let only is necessary if we do x equals 10 colon integer here. Okay. Ooh, sorry. Let's go ahead and do that straight up in this and copy that. Okay. There we go. So we now have x is an integer. Let me go ahead and unset types, because I don't need necessarily this to be there. So now if I do let x equals 10 colon integer again, you won't get that. But if we do type t, you'll see that it is an integer. All right. Any function now that you provide x to, all right, like you specialize it, like let's say you're doing partial function evaluation, that type signature will automatically take x's most restrictive type, and it will adopt it in the function signature if the type that x is representing satisfies the type class of the operator that you're specializing on. Okay, so let's go back to, again, the arithmetic operators, okay, like times or even multiplication or addition. Okay, if we decide to do x times, you'll see that this specialization, all right, on x takes the most restrictive, because integer is more restrictive than numeric, and uses that in the left associative manner to actually go and determine what the function signature should be. All right, and this is regardless of what location it's in. All right, because again, although things are left associative, and the leftmost argument actually determines the function signature, in terms of specializations, the most restrictive type will end up actually determining what should be used in order to create the function signature, all right, and it be type checked against, okay, because you want to make sure that all your types matches the most restrictive type in the case of your generic type variables, because otherwise you're going to get a violation later on in the execution of your code. So we could use this kind of information to create more restrictive versions of our operators. Like, you could certainly create an add function that only says add integers, where you are restricting the operator on the integers that you're providing, okay? And you'll see here, actually let's do this here instead. I think you'll get the same thing. And if you do t of add integers, you'll see that you'll get a function there. But you can't actually generalize from a more specific version. You can't start with an integer and then go back to a numeric type class, because you'll end up getting what are called you lose some generality when you're attempting to actually go from the representation, the most restrictive representation, to the most general. Because although that most restrictive representation may implement the type class that you're actually restricting on, you'll get ambiguous type errors saying that you can't find the types and they don't necessarily match. An example of this is let's say that we have our good old friend, the identity operator, right? And we decide to say, you know what, we're going to go ahead and make a identity operator specifically for. We're going to restrict the identity operator specifically for numeric types. Okay. Now, this is valid. This can actually work. Now, let's say that we want to go in and just say, hey, you know what? We need to be even more restrictive. We're going to take the identity operator, which we restricted on numeric types, and we're going to say, you know what? We're only going to deal with ints, right? If you attempt to say at some point, or somebody sees this and says, you know what? We want to create this and go back in the other direction. If you attempt to even create an error, a function like this, all right, the reasons why you're going to get this error, which is can't find type A1 with int, is because the type that you're restricting on, int, is already a very rigid type variable, right? It's not, you cannot generalize it to go in the other direction, and as a result, what's still going to be inferred by the type inferencer, by the Haskell type inferencer, is the most restrictive type, which is the definition of int ID, not of the numeric type class constraint being applied to a generic type variable. All right. This is a very subtle but very important piece of the puzzle, because of the fact that it's basically telling you it's okay to start generic and then go restrictive based on your cases, but if you're starting restrictive and going the other direction, you may end up having to implement some stuff. You can't use the underlying Haskell machinery to generate the more restrictive version, or sorry, in this case, the more general version of your code, because you've already provided a more restrictive version of it. All right. That's kind of the rule of thumb. Like, if you know that you're going to probably deal with a variety of types, it'll be better to write your code against a type class than starting with the most restrictive concrete type you could think of and then go in the other direction, because you're going to probably end up, in the first case, you can simply use Haskell's generation mechanism to restrict the types against a particular type signature. So you could take a generic algorithm and then say, you know what, let's write an alias like we did with numeric ID and restrict that generic algorithm against a particular type class or a particular type. Whereas in the other direction, you're going to probably end up having to rewrite the algorithm as a generic algorithm and follow it again. You may end up having to reclassify it again. One requires a little bit more refactoring than the other, so I'll leave it to you to decide which is most appropriate. It might be a case-by-case basis as to which one's a better approach. Personally, I think starting generically with a type class would get you much farther and allows you to then leverage the existing machinery of Haskell to actually restrict your signatures for better type safety than trying to start with a specific type. Although what it enables you to do is essentially to explore the space of particular types that you might actually be dealing with. And who knows, you might end up realizing that your generic algorithm will handle almost 80 to 90% of all your cases, and you don't have to actually go and implement a more specific case. All right. The next type class, and I'm going to just breeze through some of these just because we've actually encountered these a lot, is the ordered type class. Again, we talked about this briefly earlier. Let me actually go and delete this guy so I can get my REPL back. And you can see that ordered is actually implemented for a lot of different types. But the ordered type class requires that you also implement the EQ type class because it's used for the comparison operators, including less than or equal to and greater than or equal to, and the min and max, as well as the comparison operator there that will determine whether or not one is greater than the other, and it will actually give you a it won't give you necessarily so the compare operator basically tells you whether or not something is greater than or less than or equal to, but it uses an enumerated value to determine what that is. So for example, if you pass in compare 4 and minus 4, okay, you end up getting that 4 is greater than minus 4. If you compare 7 and 8, you'll see that 7 is less than 8, so forth. And if you actually look at the type that's being passed in, that's being returned by compare, is you're getting this ordering enumeration. Okay. This also tells you that there's not necessarily going to be a less than or equal to or greater than or equal to operation in this ordering enumeration. So it gives you some nice things to actually go through and see what would be most appropriate. But all the other operators as part of the ordered type class, they all return bools. Okay, as you can see by the signatures here. Then obviously ordered also deals with then min and maxes, because now you can actually deal with min and maxes, and these are taking generic operations as long as there are specializations on top of them. So in the case of, say, strings, you have where is it? You can actually compare two strings together, and you'll end up getting an interesting so compare Julie, Chris. You'll see that Julie is greater than Chris. If you actually do max between the two, because those types are a list of integers, and characters have an implementation of the ordered type class, you can certainly go ahead now and use this. This is giving you, for folks who are unfamiliar with this comparison about using min and max against strings, is giving you a lexicographic ordering of those operations. So if you look at ASCII characters or even Unicode characters, you could see in the location of where in the alphabet that J is obviously going to be greater than C, and that's what's leveraged to actually go and give you that comparison. One thing about these operations, just like everything else, they are operators that take in two values and then return a signature, which means if you're trying to adopt this for multiple values, or you're trying to do like 3 or more, you're going to have to nest the operations in some cases, or you can certainly write a more complex algorithm that will go through a set collection. So like in the case of 3 numbers, you might write something like max of 7, 8, and 9. We both all know that's going to return 9. This nesting is possible because of the fact that you're returning the integer of the previous one that's becoming the input of the second one through the composition. If you okay, sorry, there's a just looking at my notes here just to see if there's anything else I want to discuss related to ordinals. Okay. So one thing to note is derivations for data types that use uh, any of these type classes it's going to be relied on. It's going to be relying on how you defined that particular data type to determine what would be the most appropriate implementation for a particular type class. Okay, to give you an example of this, and we talked about deriving a little bit in not too much detail, but this is again as a review. Recall that some of the built-in type classes can provide you default implementations for these type classes if you use the deriving keyword to actually derive the particular classes. So if you use, say ORD here, this will end up generating a specialized implementation of the ordered type class against the day of the week type that we specified here. And if we go in and look at info ord, you will now see at the top of the listing now our ordered day of the week here, as we saw normally when we defined our own implementation of the type class. We end up getting this same signature of the instance. The one thing to note though is since this is generated, the sum type, the order in which you define the sum type is the order in which the implementation is going to take in order to implement the comparison operators. So in this case, our minimum, if we use min between Monday and Tuesday, okay, you'll see that it will return the day of the week function. Why is it not actually returning a value? Max 1 Tuesday. It gives us a function of the day of the week. Let's do less than Tuesday. Yeah. If we use the comparison operators, it looks like the max and min isn't doing what I expect it to do. But again, looking at the minimal, it looks like it only implemented the comparison operators and the less than or equal to. So it didn't actually, it may not have implemented max and min the way I expected it to. It's just returning some sort of day of the week in order to determine what it is. It's just a signature. what the return value is going to be. And you can use all of this stuff that's already defined. You could see that if we use Saturday and Monday, you could see that Saturday is greater than Monday, and so forth. What this generated, though, is it's based on the assumption that, because again, ordered is implementing essentially equality, so you can actually use one now, and you'll end up getting true and false. It may not necessarily, in our case, it may not necessarily leverage the generated EQ type class interface. It may end up actually implement it may actually prefer our day of the week customized EQ type class instance versus what's being generated or not. That's particularly important, particularly useful to actually be aware of. But the ordering that it generated is based on the assumption that the leftmost argument is going to be your minimum, and the rightmost argument in your data definition is going to be your maximum, and then everything else will just fall into place. So the one thing that this particularly restricts us to do by using deriving is if this is how you want to assume stuff, this is great. You can actually leverage this. You don't have to generate anything. You don't have to write anything. No code maintenance and all that. And it will. The compiler will. The compiler will handle all that that type inferences for you. Now, because of this this ordering, some restrictions are definitely applicable and must be aware of. One is since there's no flexibility in actually defining, for example, that one of the days are particularly more important than the other days. Let's say, for example, we want to implement Friday has always being the best. All right, we might actually use this to. You might actually end up leveraging this by first implementing. Oh, that's the reason why this didn't work. Let me see something. Show. I think I needed to show in order for me to actually min Mon Tuesday. Yeah, that's the reason. Max Mon Tuesday. It's because I needed to show to implement a string. That happens sometimes. Okay, so let's say that we want to go and make Friday the most important day of the week. All right. We might end up implementing just a show because again we've already defined in our thing our instance, our EQ instance. We just need to now implement our own instance of ORD, a day of the week, where now if you recall what we need to do here in order to implement our ORD is we need to implement either compare or less than or equal to, all right? So let's implement compare very quickly, all right? Compare basically has a signature that tells you, gives you 2 days of the week and provides an ordering, okay? So if we get Friday and Friday equals EQ, we can do Friday and anything else equals EP, compare anything else on Friday equals LT, and compare other two. And they are EQ to each other, all right? It doesn't matter about the priority, all right? So if we go and define it this way, we'll end up getting now that, min, mon, and Tuesday, max, mon, and Tuesday, everything is good there. But if we start using compare, mon, on Tuesday, they're going to technically be EQ to each other because it doesn't matter about the priorities. But if we compare Monday and Friday, we'll say Monday is less important than Friday. But if we go the other way around, we'll say that it's greater than, and so forth. Right? So we now essentially defined our behavior by deriving, by implementing our own instance of the compare operator against the ordered interface, and we can actually go ahead and leverage it as is. All right. So let's write a generic function that takes in like in Lisp, we have the EQ function that takes in any two values. All right. And returns a boolean whether or not they are EQ or not. All right. If we do EQ on two generic types and we try to compile them as is, you'll end up getting the following error. We've already covered this. We've actually covered this because, if you recall, A is a generic type that doesn't provide enough type information to look up a proper instance of the EQ type class to see if it's defined against that concrete type. And as a result of that, you end up getting this error saying that we can't actually figure out what type you're talking about. So from using the equals equals, so you're going to have to provide some sort of type class constraint against the type variable that you're passing in. But let's say that we decide that the only thing we need to worry about is it being ordered. Well, now we it's compiling, but why is it compiling when GHC is asking for EQ? Well, remember when we covered the ordered interface, we know that the ordered interface itself has a type class constraint before it can be instantiated, and that is the fact that whatever type that's passed in must implement the EQ type class interface. So by having something ordered, you're automatically saying that that's going to be EQ, and that's why you will end up being able to use in any places where you require equality, you could use actually an ordered type too, and you'll get the same thing because EQ is a superclass. All right. But this goes back to what I was saying earlier when we're talking about type class constraints, and that is you want the minimally sufficient set. You want only the amount of operations that you need in order to implement an algorithm to make it type correct. You don't want to go in overhead in this case. And in this case, this is a little bit overkill because of the fact that we're not necessarily using the less than or equal to operators, we're just using the equals operator. So you want to actually end up doing this. But the other one doesn't actually hurt because of the fact that ordered implies EQ. All right, we have type class inheritance, and we have superclasses between different type classes. Okay. I'm going to just briefly breeze through enum and show here, just because I think enum is less interesting than show, but I'm just going to mention it because it has a bunch of interesting functions. Enums is dealing with enumerations, which means, as you know, this type class will deal with sets that are enumerable. So that is, those are sets that are ordered in a particular way where there is a predecessor to one value and a successor to one value and so forth. Um, and This information tells you that we have specializations already available to many of the classical types already available built into the type system for Haskell. So, for example, there is a successor function for numbers, numeric types. You can see a successor function for even floating point types. A predecessor function for floating point types, even a predecessor for your characters and so forth, because these are all very basic things that can be defined very, very quickly for enumerations. Any new ones that you're defining, you need to just minimally define to enumeration, and from enumeration, you'll get the other functions for free. If you end up using So a couple of interesting functions here that is particularly useful to note is functions that are taking in a value and returning a list. Okay, here you can see these functions here are returning a value from a list. All right. So if we end up doing to from enum Monday. Actually, it doesn't implement enum. I forgot about that. I should technically write that as an enumerated type, but let's try the list types here. Let me go ahead and print out the so that we don't have to constantly move through it. If we try, for example, enum from den, this actually creates a list type for you for enumerations that you could then leverage. In this case, it's going to be a list of integers. If we do 1 to 5, you'll end up getting. Interesting. This is not what I was expecting. Not enum from den. Enum. I think I'm printing out the wrong thing. Hold on. There's an issue with our. Let me put an error here. Just to make things a little bit easier. Okay. Okay. There seems to be an issue with, here we go. For some reason it just kind of messed with my my REPL, which was causing some issues. So sorry, I was having some technical difficulties there. So what was I trying to show? Oh yeah. So I was using the wrong one. I was one creates an infinite list and one has an upper bound. So enum from 2, if we do 1 to 5, we'll end up getting a finite list type of 1 to 5. You can also use this not only for integers. You could use this for any type. So you can use this from 2 and provide a list of characters. But by the way, that a list of characters alias to a string, so it returns you a string itself. What we saw with the other one, because there's 2 additional ones that we need to talk about, and I was ready to talk about enum from den. But now that we have this, we can actually talk to this. Enum from den and enum from den 2 are 2 different functions that will create one. It creates a finite list and one creates an infinite list. The one that I was running earlier is creating an infinite list automatically for you, but we really don't want that to run itself. So the easiest way to illustrate this one is let's say that we want to create a list of evens. All right, we could certainly do that by starting enum from den, starting with 2, and then what this is taking, the first argument is the initial value, and the next argument is the increment. So by doing this, we now have a set of infinite even numbers, and if we just want to grab some stuff, we could just use take to grab the first 10, and it'll give you the first 10 even numbers. Enum from den 2 basically is a finite version of this kind of, hey, we want to only create a finite version of this set up to some upper bound. So you could certainly say the first argument is your initial value, then your increment, and then what you're returning has your upper, and we'll go ahead and create that finite list type for you. The one thing that's slightly different about enum from den 2 than what you're normally associating with creating an incremented collection. So you might be thinking, oh, this can create any sort of collection, but what you really want to understand is what enum from den 2 determines the actual increment based on the first argument and the second argument. So in this case, the increment is going to be 10. But let's say that we use enum from den 2, 1 to 10 to 100. Our initial value is 1. Our second value is going to be 10, but then you're going to see that the increment value is actually going to be slightly different, and that's because the difference between these two is 9. So your increment up to 100 is actually going to be 9, not 10. So you'll start with 1. 1 plus 9 is 10. 10 plus 9 is 19, and so forth. All right. In this respect, enum from den 2 should not be dependent on, in order for you to create these kinds of finite collections. You might actually be better off using something like, say, take 10 or take while to actually go in and grab those operations. All right. And take is just nothing more than a function that takes in a number of values that represents the collection size and an infinite collection, and will create a subset. And it can actually be a finite collection too as well. So if you have, like, say, in this case right here, our enum from den2 of 0 to 100 based on tens, if you do take 5 $sign enum from den to 0, 10, 100, this is only going to give you the first 5 of that collection. Okay, so it can take any collection of any size. It's typically used for infinite collections, but you should certainly use that to actually go in and leverage and create subsets of your infinite sets. Okay. Enum from den2, I'm still not entirely sure when enum from or enum from den2 or enum from den is used on a day-to-day basis. I'm still looking into that. But I think the to enumerations and from enumerations certainly will help, especially if you have like days of weeks or other enumerated types that could certainly be used to go and convert between one versus the other. So let's talk about show. We're almost done here. So show is, as you saw earlier, that caused that one issue with our type class of not displaying our day of the week. Show actually is what's leveraged to create human readable versions of your data, right? So if you're implementing something and you're trying to convert it into a string, you're going to have to implement the show type class in order for you to generate string values, and that's ultimately what is hooked into the terminal. All right. Had we not implemented show this way, we would have had to implement show for our day of week manually, and we could certainly do that. Let's first talk about what show is. So what implements the show type class? Okay, a lot implement the show type class, but what defines it? Well, we can see that show requires 3 functions. Show PR shows precious, which takes an integer and a value and then returns a show string. The actual show function that takes in any value and returns a string, and then show list. Okay. One thing to note is show is not dealing with serialization. Okay, serialization is dealing with how data is actually structured in either a textual binary form for essentially retrieval and persistence or communicating with other computers. All right, show is trying to figure out only human readability. In another way of saying it, the show type class for our common Lispers or Lispers in the audience, it's actually implementing pretty printing. All right. That is its only job, and that's the type class's only job is dealing with pretty printing. How do you print something so that it's human readable in the console, and not deal with anything else. All right. Show is a particularly difficult type class to really discuss, because when we start talking about show and we talk about printing in general, we are talking about essentially I/O. All right. Show specifically printing calls a function called print, and that actually returns an instance of the. And I'm just introducing this concept. I'm not going to discuss it until we get to that point of it. but it's essentially implementing the IO monad. All right. Specifically, show behind the scenes invokes a lower level Haskell function called print, which you can actually see here. We just type in print. Print takes a show and a type that implements the show type class, and then it returns essentially a function that takes in that concrete type and returns the IO monad, and that's how essentially stuff is getting printed into it. All right. In order for us to discuss this a little bit to the point before we actually introduce monads, and I'm again not going to talk about monads in today's discussion, we need to first remind ourselves what Haskell is. All right. Haskell, in many respects, is actually it advertises itself as a pure functional programming language. I say advertise merely because of the fact that when we get to monads and I/O, you can see that there's a solution to dealing with side effects. Okay. So, but what is a pure functional programming language? We've talked about this with respect to the lambda calculus, and we've talked about this with respect to other programming languages in this meetup. But to remind you, a pure functional programming language essentially is a programming language when you're dealing with essentially mappings. Okay, we're dealing with functions that take in some value and return some value. Okay, the pure part comes from the fact that since you are dealing with mappings, you're essentially guaranteeing through this feature called referential transparency that the same value passed into the same function will return you the same result. All right. That's where the pure comes from. The state of the system is going to stay the same even though a new value is computed based on the input that you passed in. Okay. This is very important to understand. Being a pure functional programming language and dealing with pure functions means you are guaranteeing that you are just computing results. You're not doing any hokey pokey stuff behind the scenes to change the state of your computer system. All right, that's a concept that many languages kind of bypass for efficiency reasons and other reasons as well. But it is something that you should almost work towards, because of the fact that you're minimizing the amount of state transitions and side effects that you're dealing with in your system. Okay. Why is that important when it comes to something as simple as printing some stuff to the screen? Well, printing stuff to the screen is a form of changing the state of the system, changing the state of the world. All right. You're not actually applying a function to the arguments that are passed into its scope and actually returning some sort of result. All right. You are actually manipulating the underlying universe in order for you to actually provide a result. For all intents and purposes, if you really think about functions that print something to string in other programming languages, whether it be C++, Python, or what have you, technically printing something to the screen is a void function. Okay, it's not actually returning anything. It's not mapping anything to some sort of subset of values. Okay, and in this respect, because it's not returning anything, but it is still returning something in terms of displaying something to the screen, this is what's called ultimately a side effect. Okay, it is an observable result that's separate from the actual computation. All right, and the value of the expression that's being evaluated. All right, the return value of the expression that's being evaluated. Haskell actually deals with this separation of states, side effect, effectful computations, what they call it in the Haskell book. I think other things just saying dealing with side effects is through a design that preserves pure computations in ways that can also preserve also safety and predictability of the function evaluation. Okay, and the way that they do it is through this, much higher level concept, which we'll be addressing in a bit. Okay, this is what kind of sets Haskell apart from other languages. They basically isolated these effect-bearing computations. These It's essentially the very notion of actually say isolating a computation in such a way that you know that effects are going to occur, but these effects can be composed with each other and easy to reason about is allows you to be able to reason quickly what the state of your system is during the course of computing something while verifying its results, and you can actually debug the state transitions, the transitions of the state of the world, as you are actually allowing this side effect uh, uh, computation to execute. Okay, and make things a little bit more predictable in the world of actually dealing with side effects. All right. Um, is that better than some of the other stuff that we've encountered in other programming languages? That's, for me, remains to be seen. But when I've encountered this is a particularly interesting design metric by actually that we can leverage to see what Haskell brings to the table, and that's a particularly useful thing. So when we see show and print here, it tells you that it outputs any particular, the fact that it's actually returning an IO monad here tells you that it's outputting any particular value that's being passed in to some sort of device behind the scenes. That's what's encapsulated in this IO open paren close paren. Okay, it instantiates essentially a device that's then wrapped into a functional world that will take in a value and then return another IO monad with that state being changed. All right. But in order for this to occur, you need to actually create something that is printable to show. That is, it has to implement whatever is passed into something that can be, outputted into the IO monad. All right. And the way that happens is we need to go in, and if we go and look at this again, we need to go in and implement essentially show to take in anything and print in a string. So this is what we'll do. Again, as this reads, show the minimal implementation that we need to just do to actually implement this interface is actually take in anything and show a string. So let's go ahead and do that for our day of the week. So we've already implemented, so we're no longer going to use this deriving for now. And what we're going to do is we're going to create a week instance where, and we're just going to go ahead and implement the show functionality, right? Show of mon, we'll give you mon, and then we need to just go ahead and implement this for all the days of the week. Okay, so I'm just gonna copy this and quickly implement this. Okay, I think it's shoot. What's the way that I did this? Actually, you know what? I'm gonna quickly do this in a different way. Let's grab this. I'm gonna use a little Vim foo to actually quickly whip this up. Okay. So go here, substitute the pound with equals and a new line. Okay, but hold on one second. Pound equals is new line. There we go. And let's indent this a little bit more. Let's go ahead and see if we could get this indented. Okay, then we go do this. Show that's done. Go equal sign here. And quickly do this. Use Wednesday, Thursday, Friday, Sunday. Okay, so we now have our oops. Let's my apologies, for some reason I accidentally deleted the declaration. Show day of week. Okay, now we can load this. Okay, so we now have our own redefinition. We could see this when we do show again. At the top, we can see that show day of the week is here. And we can go ahead and now leverage it. So when we say print mon, you'll end up getting mon. And you can see that this is slightly different. So if we wanted to change this to being the full day, for example, okay, so there was a comment about okay, so one of our members talked about using info on some other function that uses IO monad. I'm not entirely sure of what else uses IO monad. I'm still exploring some of that stuff. So if there's one particular function that you want me to see that shows that implements IO open paren close paren, I'm open to suggestions. Let me finish this example, and then we can talk about that. All right. All right. So we now have this. One of the nice things about this is, since you have flexibility to do anything that you want here, so you can actually go ahead and do this. You could have a short name and a long name when you're printing it out. Although, this might piss some folks off. But now that you have this, you can actually go ahead and change it, and it'll go ahead and print days of the week for you the way you're expecting it to. And it'll, obviously convert it to a string that you expect it to, and then call the print function, and print will take the string and then return an IO monad. All right. So what is this IO monad that I keep bringing up and that's brought up in this printing function, right? Well, it's an implicit. So first off, we've actually encountered this in a couple of places. If you recall, in our I think it was in our string concat example. Yeah, in a string concat example, we've encountered this with this IO monad, that it's a function that returns IO monad itself too. And it's because of the fact that, recall that since we're essentially printing some stuff and we're putting strings into the console, we are essentially creating side effects. So this is the only thing that main can do. It's going to be producing only side effects, so it's going to have to return the IO monad. But what is this? What is this guy? This guy is nothing more than an action. You could think of this as an explicit declaration that something is going to be performed, right? And it's out of our control. It might be executing outside of Haskell by some interaction with, say, like the operating system, our host operating system. It could be talking to the network. It could read from the network. It could do reading and writing to the file system, what have you. All right. Bottom line is though some action is actually going to occur. And when that occurs, it will, that action is going to uh, be encapsulated by and be returned. It'll contain some sort of return value that's then actually returned to the user, but it's returned in a has an has another instance of this action. All right, to take in the next action, if you will. All right. Um, the empty tuple is available in that signature because it is returned. It is a value that essentially um, represents nothing. Um, since printing something to the screen doesn't have anything meaningful in terms of return value, um, it needs to be either void or but show something. But void is actually very explicit inside of Haskell. So what the IO action does has, like any other expression, is it returns. It's a normal function. It's like any other expression in Haskell. It doesn't just return nothing. It will return essentially the empty tuple at the end of the IO action. So this is actually specifying essentially what is ultimately returned. You're doing some sort of IO, and then your return value is this empty tuple. All right, this is how I understood how this works. So when you're calling print in this case, when we're using to go back to our TC example, when we call print on any of these enumerated values as part of our day of the week thing, what's happening is this action occurs. All right, it prints to the console, but it doesn't actually print to the console and then just do what most other programming languages do, in that it returns back to the execution of the program. No, what it does is it does the action and then it returns the empty tuple. All right, so this is why that empty tuple is part of that. Does that make sense for folks? So to review this is the print function first performs the action of printing to a string, then completes the action, marking the function execution's completion. Okay, and the empty tuple is then returned to as part of the the limitation of the side effects here. All right, and that empty tuple is what's ultimately going to be constructed, but it's not actually the thing that looks like the return value of the IO. Is just that it's some metadata saying that, yeah, I'm returning nothing here, but really some action has occurred behind the scenes. All right. The reason for this is actions represent something very different in Haskell. Okay, you can think of an action as representing a formula that's taking in that's a factory that's producing something. All right. So if you actually provide a type, to an action, and we're using actions because the Haskell book and other books on type classes explain it closely this way for monads. You're basically saying that that type that's being returned for producing something may require side effects before you actually get your final value. All right. So if you use, say, IO string, okay, what you're actually saying, if you have a function that, let's call this, f, okay, and it's returning an IO string, what this is actually saying is, by the way, I'm going to be returning a string to you ultimately, but in the course of me returning this string, all right, some side effects might be occurring behind the scenes. I might be printing errors to the console. I might be writing something to the network. I might be doing something behind the scenes to some sort of output device or input device, okay? And all that stuff is happening, but at the end of all this computation, of all this stuff, the final value that I'm actually going to be returning is a string. So in the case of I/O, when you're printing something to the string in terms of a terminal, that's the same thing. It is saying that I'm returning you a tuple that has nothing in there because there's nothing to return. But in the process of, before I return this tuple, I'm going to be doing a bunch of other stuff. Okay, when we get into monads, you're going to start dealing with this a little bit more. But because we need to be a little bit more practical in printing some stuff to the string that's being introduced at this point, I really don't want to dig into it much further than that, just because I don't think it'll do us justice to actually start going into monads before we dig a little bit deeper into the patterns that are inside Haskell, and it's a gradual growth to get to a point where you can start talking about monads. There are a couple of other concepts that you need to understand before you can start doing it. But that's what that signature is telling you, all right? That IO open paren, close paren signature is essentially telling you, I'm doing IO, and your final return value is of this type, which is the unit type, or the empty tuple, right? I'm going to stop here, and I'm going to ask, are there questions? Okay. So what we've now seen is we've implemented our own type class, show type class, and as long as you implement the show type class to convert your types to strings, all the underlying machinery to print will work for you for free. It just because all those require just the show type class to be available. The final type class that that we're going to be talking about is actually a pretty interesting type class that I didn't realize was there, but it's here anyway. Is the read type class. What that is the name is pretty self-explanatory. It is reading a value and then has a string, and then it's going to return a value for you. Okay. So, and again, in order for us to implement this, you just need to implement either reads press or read press in order for you to actually understand this. And this has started going into some other stuff in terms of parsing and stuff. But again, like show, where show is displaying strings and dealing with standard, output, this is essentially dealing with the standard inputs, taking in a string and then going to return some sort of value to you. Read, like show, also doesn't deal with serialization, okay? The problem that arises with read sometimes is since how we define strings deals with lists, read has to handle the empty list, and there is an issue where um, something being readable that's taking in a string and returning something given the signature that we see here. Um, there's no real way for read to actually do what we're expecting it to do, right? And we can see this when we do um, something that is readable. It's going to take in a string and then it will return a value, because how do you handle, for example, the empty string on and how do you handle the empty list um, for string? Um, I'm not entirely sure that that can work, because of the fact that it depends on the type that you're dealing with as to whether or not it's going to be a valid or not valid thing. An example of this is integers. If you're reading in integers as strings, all right, 1, 2, 3, 4, and you say that I want you to return an integer, this will all work, right? But if you just pass in this as an integer, you're going to get an exception. Okay, you're going to get an exception because there's no way for read to be able to recognize that, and that means that in many cases that because it's throwing an exception, the way prelude works for the read function, for read type classes especially, is that read is implemented as a partial function, but doesn't return a proper value for everything. There are ways of dealing with this, but this chapter that we're covering and in other books, in order for us to fix it based on what I read, requires you to do some additional machinery. And again, it goes back into some of those higher order concepts that we have not yet visited yet. So I'm just briefly mentioning to here, just because we're going to go and quickly implement. Actually, I don't know if I can implement this without some of those higher order things. Let me just double check this here, just to make sure that I'm not messing it myself. Yeah, I'm gonna have to start leveraging some of the parser combinator stuff here in order for me to properly implement this. This is going to be requiring a little bit more detail. So we're going to hold off on actually dealing with implementing the read type class for now, just because it requires a little bit more concepts. But just beware that when you're dealing with at least the built-in types and you're doing reads from strings, that read will throw an exception for invalid parsing, for parses that it cannot understand for the type that you're trying to convert to, right? We've already talked about type dispatch multiple times throughout today's discussion, right? We've mentioned just briefly what exactly it does. Type classes itself dispatch on type, and what that means, it takes the concrete types, checks to see if it fits into a particular type class constraint. If it fits all the type class constraints within some higher level type class that uses type class inheritance, then that type class gets instantiated. It gets validated. It checks to see if that concrete type has implementations of all the functions for that higher level type class, and then it'll execute the operations based on that type class that it satisfies. Okay, and you've seen examples of this all over the place with numerics and the additive types and so forth, right? In this case study that we're going to be talking through, and I think this is a particularly interesting one, is it's going to encapsulate everything that we covered so far. Actually, you know what? Um, just realized that this is going a little bit over than what I want to expect, and I want to really cover this case study. Um, I'm going to hold off on this. Next time um, I know we're going. I was going to talk to you about type dispatching, but this is a case study of defining that I think we should really dig into and just go walk through, and that is it's going to define a type class that we've defined ourselves. All right. Then we're going to create instances of types that have of that type class, and then go ahead and then see how those instances use the functions in the type class. So I'm going to end it here. Um, are there any additional questions from our audience? Okay. Well, in that case, I will see you all next week. We will be completing our final discussion on type classes, and hopefully we'll get started on dealing with some other interesting topics inside of Haskell. So thank you for your time. I hope you all enjoy your Memorial Day weekend for folks in the United States. Otherwise, folks outside international, um, enjoy your weekends, and I'll see you guys next week. See ya. Bye.